Welcome back to Dry's lecture. This particular topic that we are going to discuss today is called direct torque control. Direct torque control actually allows you to control AC motor drive without really knowing the actual flux vector position, the stator flux vector or air gap flux vector position in the case of an AC machine. So in direct torque control, basically we start with the expression of the torque. So electromagnetic torque of any AC motor drive is given by K times whatever is the flux linkage of the stator side and flux linkage of the rotor side and sine of the angle between these two flux linkages, that is the stator and rotor flux linkages. So if we are able to adjust the stator flux linkage or rotor flux linkage magnitude, or if we try to adjust the angle between them, which is gamma, then it is going to modify the magnitude of the torque. This constant K depends upon maybe the mutual inductance between the stator and rotor. And also it depends upon the number of poles. So these things play a major role in deciding what is this constant value K. If we are really looking at not touching the flux linkage values at all, only modifying the electromagnetic torque, then we should be able to just modify this gamma and the angle between stator and rotor flux linkages, and that is what really decides the electromagnetic torque. But if we are really interested in adjusting both the flux values as well as the torque value, then we should be adjusting psi s, because psi s is the one which we can control directly. As you know, we can say d psi by dt is generally the voltage, induced EMF. With a negative sign, just to indicate that if the flux is increasing, always the the tendency of Lenz's law essentially tries to nullify the change that is happening in the flux linkage. So that's why we put a negative sign. So the induced EMF will work towards reducing its own root cause, which is actually delta psi itself. The variation in flux linkage itself. So if we say d psi by dt is V, we should be able to say psi is equal to integral of V dt. So this is going to tell you basically that if I want to modify the stator flux linkage, I should be modifying or appropriately adjusting the voltage that is applied to the stator side. So for direct torque control, we are going to manipulate the flux linkage of the stator directly by adjusting the voltage. So this is one of the major differences between the direct torque control and field-oriented control. Generally, what we see is in FOC, we deal with currents directly. And we also need to get the exact position of psi, which is the flux linkage. Whereas in DTC, what we are looking at is we deal with the voltage. What voltage we are applying to the stator side. And we don't need the exact position. We need to know in which sector, the 60-degree sector. That is, if we divide the entire 360 degrees into, let's say that we look at the flux linkage vectors as 6 such positions that is being occupied probably. Okay, so we divide this entire 360-degree into, let us say, 6 sectors. So we are going to call from here, from this portion until this portion. So this is going to be sector 1. And from here until here, this is going to be sector 2. So like this, we will have 6 sectors. So all we need is to know the sector position. We need not know the exact position of the flux linkage, but which sector it is occupying. Is it sector 1, sector 2, sector 3, and so on. So all we need to know is the sector position of the flux linkage vector. So in that sense, the calculations needed are much less. That is one major advantage. And it gives you a good dynamic response because the calculation required is not so high. So let us now try to see how exactly what we mean by direct torque control and how we exactly implement it. So as I just told you, we are looking at applying a voltage. So we are going to apply a suitable voltage to ensure that torque demand is met properly. This is the crux of direct torque control. So what we are looking at is DTC. So in DTC, the primary aim is to make sure that a suitable voltage is applied to make sure that the torque demand is met properly. So for this purpose, first of all, let us try to look at a voltage source inverter. So we are going to look at VSI based implementation of DTC in an induction motor drive. So that's what I'm going to deal with in today's lecture. So how a VSI can be used to implement direct torque control in a 3-phase induction motor drive. So let me first of all take a VSI, 3-phase VSI and 2-level VSI. So we are going to have one switch like this, one more switch like this in A phase. This is going to be the second leg, which is corresponding to B phase with 2 switches. And this is going to be the third leg, which is corresponding to C phase. Now we are going to have from here and from here and from this point, we are going to have the 3 phases of the induction motor drive connected. So let me show this as ZC, this is ZB, and this is going to be ZA. So we are looking at this as DC voltage, which is VD, let us say, and we are going to have the switches named somewhat like this. This is 1, this is 4, this is 3, this is going to be 6, and this is 5, and this is going to be 2. So this is going to be ZC, which is the C phase impedance. This is the B phase impedance, and this is going to be the A phase impedance, and I'm going to call this as neutral. Okay. So we can say that the switch in A phase, if I may call this as A phase, this is B phase, and this is C phase. So A phase switches are 1 and 4. And if 1 is closed, I'm going to call that as the position of the switch is in 1, whereas if 4 is closed, we are going to call that position as 0. So whenever positive switch is closed, I call that position as 1. Negative switch is closed, that position is called as 0. So the same way in B phase, if I try to look at it, it can be 3 or 6. If 3 is closed, I'm going to call that position as 1. B phase position is 1. Whereas if 6 is closed, I'm calling this position as 0. The same way for C phase, if I am going to have 5 is closed, then I'm going to call that position as 1. And if 2 is closed, I'm going to call that position as 0. So if we say by chance, maybe 1, 3, 5, all of them are closed, literally 0 voltage is applied across the induction motor. So if I say 1, 3, 5 closed, then I'm going to have 1, 1, 1 as the position. This is 0 voltage applied across the induction motor. The same way, if I have 2, 6, 4 or 4, 6, 2, they are closed, it is going to be 0, 0, 0. Now again, this is also corresponding to 0 voltage being applied across the induction motor, because either positive leg is connected directly to all the 3 phases or negative leg is connected to all the 3 phases in these two cases of 1, 3, 5 or 2, 6, 4 switch position. So literally 0 voltage is applied across the induction motor. Whereas if I look at rest of the positions, it can be 6, 1, 2, 1, 2, 3, 2, 3, 4. I'm looking at 3 switches conducting at a time, something like 180-degree switching mode, what we talked about in VSI. Then 3, 4, 5, 4, 5, 6, 5, 6, 1, and of course 6, 1, 2. So 6, 1, 2 in this, if you look at it, this corresponds to B phase, this corresponds to A phase, and this corresponds to C phase. So if I try to write how A, B, C positions are in this particular case, I'm going to have basically 6, which is corresponding to B phase is 0, and A, which is 1, that is 1, and C phase, which is corresponding to 2, that is also 0. So this is 1, 0, 0. Same way, I should be able to write what is 1, 2, 3. 1 is A phase, which is 1. B phase is 3, that is 1. And C phase is 2, which is 0. So the same way, let me write this. This is 0, which is 4, corresponding to A phase. Then this is 1, which is corresponding to B phase, that is switch number 3. And this is 0, which is 2, corresponding to C phase. Then 3, 4, 5, I'm going to have 4 is 0, A phase, then 1, 1. Then 4, 5, 6, that is going to be 0, 0, 1. And 5, 6, 1 is going to be 1, 0, 1. So I'm essentially showing these are corresponding to the switch positions, which are either connected to the positive side of the battery or negative side of the battery in ABC phases respectively. So if I am looking at 612, so let me first of all draw the circuit of the inverter in such a manner that I am able to, just show 612 being on. So this is VD and 1 is on. So 1 is going to be on like this. This is 1, which is on. And from here, I'm going to have A phase ZA connected. And the neutral is here. So I'm going to have ZB and ZC. Both are connected like this. Now from ZB, it is switch number 6. So I can show this also closed. And from ZC, it is going to be switch number 2. And these two are connected together to the negative side. So this is the equivalent circuit corresponding to 612. When I talk about 612, this is the kind of equivalent circuit I have. So if I assume that a current which is flowing from here is ID, for example, it is going to divide itself into two halves. So this is going to be ID by 2 and ID divided by 2. So the voltage drop across ZB and ZC are going to be half the voltage drop across ZA. So if I call this as 2 by 3 times VD, which is the voltage drop across ZA, this is going to be 1 by 3 times VD. So this is the way the voltages are going to be distributed. So I can draw, if I say that normally I'm going to have the A, A phase vector positive is in this direction, and I'm going to have B and C phases somewhat like this. So I should say this is A normally, and this is going to be B, and this is going to be C. Please remember how we talked about in a generator, the windings are A will be here, B phase winding axis will be here, C phase winding axis will be here, and the magnet will be rotating in this direction. It will first face A, then it will face B, then it will face C. So that is what we are drawing this as A, B, C, we are drawing like this. Now, ZA is having 2 by 3 VD. So let us say this is going to be 2 by 3 VD. And ZB and ZC are having 1 by 3 VD. But please remember, neutral is at a higher potential compared to the potential at this point, because this is the negative point, negative terminal of the battery. So neutral is going to be at a higher potential. So if I look at what is the voltage drop across ZB or ZC, it will be minus 1 by 3 VD. So minus 1 by 3 VD, let me draw C phase voltage in the opposite sense, the same way B phase voltage also in the opposite sense. So this is going to be, what is the voltage across C phase? This is the voltage across B phase. So when I add all of them together, I'm going to have basically VD, which is coming along this direction. Okay. So I will have basically this as the resultant, what is coming up for 100 switch position, which is corresponding to 612. So for 612, if I look at the resultant voltage position, if this is the origin or the reference, this is going to be the kind of voltage I look at. Now let me take a look at this for 1, 2, 3. So I'm going to look at what happens when I have 1, 2, 3 as the voltage, the switch position. So 1, 2, 3. So when I have 1, 2, 3 as the voltage position, this is going to be VD again. And from the positive, I'm going to have 1 connected to A phase. So this is going to be ZA. And I'm going to have 3 connected to ZB, which is corresponding to B phase. Now here is the neutral. And from here, I'm going to have C phase connected. And to C phase, I will have switch number 2 connected. And this is going to close the circuit like this. So this is the equivalent circuit corresponding to 1, 2, 3. So if I have ID flowing here, I'm going to have ID divided by 2 and ID divided by 2 flowing here. And here I will have ID flowing in this direction. So this is going to be 2 by 3 VD, whereas these two are going to have 1 by 3 VD and 1 by 3 VD. So now if I try to draw again the vector, resultant vector corresponding to A, B, and C phases respectively. So I'm going to have corresponding to this, C is 2 by 3 VD, which is actually minus of 2 by 3 VD. So this is going to be 2 by 3 VD, which is corresponding to C phase voltage. 1 by 3 VD, now I'm going to have both B phase and C phase are having 1 by 3 VD as the voltage, which is actually in the positive side itself. Whereas C is in the negative side because C is carrying the current from the neutral into the phase. So it is a return current. So the resultant is going to be along this itself. So if I try to draw the resultant will be along this. So just like how I have drawn 100 here, almost 60 degrees away. At 60 degrees away, I should be drawing the next vector, which is corresponding to 110. So the same way I should be able to draw all the 6 vectors which correspond to different switch positions like this. So this is 110, this will be 010, this will be 011, and this will be 001, and this will be 101. And if I'm talking about 0 voltage vector, it should come here, and that should be either 000 or 111. So the inverter positions, what we normally see right from 612 until 561, they correspond to 6 non-zero voltage vectors. Let me call this as V1, this as V2, this as V3, this is V4, this is V5, this is V6. So the inverter position, switch positions correspond to different non-zero voltage vectors starting from V1 until V6. And the two zero voltage vectors which are corresponding to 000, this is V0, and 111, this is corresponding to V7. So essentially we have 8 voltage vectors, resultant voltage vectors from the inverter switch positions. Out of this, 6 of them are non-zero, which correspond to V1, V2, and so on. And 2 of them are zero voltage vectors, which are V0 and V7. So the three-phase inverter, by appropriately adjusting the switch position, should be in a, poised to increase the flux linkage or decrease the flux linkage, or make the flux linkage move forward or backward. And this is what is utilized for implementing direct torque control. So let me first of all draw the block diagram corresponding to implementing direct torque control. So what we are looking at is we want to run the motor at a particular speed. So we are basically looking at certain omega m reference to be reached, and the actual omega m is different from this value what we want to achieve. Now there is going to be a comparator which is actually looking at the difference between these two. So this is actually going to go to a speed controller, and this speed controller is going to give us what is the reference torque. So it is going to say this is what should be the reference torque if I want to bridge the gap between the reference speed and actual speed. Now, if I know the reference speed, I should be able to calculate what is the flux. So flux calculation, reference flux calculation is done at this point. So this reference flux calculation output is what is psi S reference. Let us say this is going to be psi S reference. Now what we are going to have is a comparator here. So we are going to have flux and torque comparator. So if the flux error is positive, that is you have to increase the flux, then you might have to add some more amount of voltage probably to your stator side so that the flux value increases. The same way, if the torque is less, then you might have to push, because normally if you look at an induction motor, you are going to have maybe psi S is here and psi R is going to be behind that. It is closely following that. And whatever is the angle between these two, we call this as gamma. And we said that psi S cross psi R, which is going to be psi S magnitude multiplied by psi R magnitude and sine of gamma. This is what actually gives you the electromagnetic torque. So if I want to adjust the electromagnetic torque alone, I should be able to adjust gamma. So for which I have to maybe make this stator flux go forward compared to the rotor side. So gamma will increase and hence you are going to have an increase in the torque. This is what we were talking about initially when we wrote the expression for the torque. So we are going to now whatever is the comparator output, whether the error is positive or negative or zero. So this is going to be delta psi or psi error. Let me write this as psi error rather than delta psi. So this is going to be psi E and this is going to be torque error. So this is going to be torque error. So based on what is the flux error and torque error, I'm going to decide what kind of voltage vector has to be applied to my induction motor on the stator side. So this is going to decide what kind of voltage vector has to be applied to my induction motor drive. So this voltage vector selection will decide the switch position. So three switches in A, B and C phases, they are going to be either turned on or turned off on the upper side or lower side, depending upon what is the voltage vector I have selected, so that the torque error and flux error will be nullified. So this goes to the VSI. The switch position goes to the VSI. And VSI is already given a DC voltage. So I'm going to show the power part here. So this is VD. Now what is coming out of here? So this is going to go to the induction motor. And induction motor is coupled to the load. So from here, I should be looking at the speed using a speed sensor. So let me write this as speed sensor. So the speed sensor output is actually going as the actual speed here. So this is the actual speed. Now, flux and torque comparator has to compare the reference values of flux and torque with the actual values of flux and torque. So this is going to be psi actual, and this is going to be TE actual. And this is torque error. What I have shown here is the torque error. It's not electromagnetic torque, it is torque error. Now, what we are going to do is to get what is the value of IA, IB, IC. So from here, what we are going to get is current sensing. And we know the exact 3 voltage vector position, the 3 switch positions, and we also know what is the DC link voltage. So we should be able to calculate what is the value of voltage. So we should say voltage calculation needs to be done. So let us say VA, VB, VC is also calculated. IA, IB, IC is sensed. So we can say integral of, we can say VA plus VB angle minus 120 plus VC angle plus 120. Rather, it is plus 120 and minus 120. So let me write this as 240 rather than this way. So I can say VC angle 240. This is going to give me what is V, right? That is going to be V alpha plus JV beta. And I can calculate the same way. I can calculate the same way. IA plus IB angle 120 plus IC angle 240 is going to give me V I alpha plus J I beta. So I get what are the currents along alpha axis and beta axis, and similarly voltages along alpha axis and beta axis. So from this, we should be able to say whatever is the incremental change in the flux linkage, that will be delta psi alpha should be equal to V alpha minus RS times I alpha, where RS is the per phase resistance of the stator winding, multiplied by the sampling interval, which is delta t. Similarly, delta psi beta, that is the incremental change in the flux linkage along beta axis, will be equal to V beta minus Rs times I beta multiplied by delta t. So I should be able to say, if I know originally the psi alpha value, psi alpha will start from 0 at every step, it can be updated. So I can say psi alpha volt plus delta psi alpha will give me what is new value of psi alpha. The same way psi beta volt plus delta psi beta, that is going to give me what is psi beta new value. So now that I have psi alpha new and psi beta new, I should be able to say psi alpha new the whole square plus psi beta new the whole square. Square root of this will give me what is psi s updated. This is the updated value. Okay. So whatever is the new value, that will be now replacing the old value corresponding to the next step. When I go to the next step, all the new values will be replacing the old value, and then updated value will be calculated at every step. The same way I should be able to say tan inverse of psi beta nu divided by psi alpha nu. That will give me what is gamma, that is updated. So now that I have the flux linkage values which are updated and gamma value which are updated, I should be able to calculate electromagnetic torque as well. So the electromagnetic torque value which is updated, that will be whatever is psi s, psi r, or rather I can say directly because I have psi alpha and the currents with me, I should be able to calculate them with the help of, it is a function of flux linkage psi alpha, psi beta, and I alpha and I beta. I should be able to calculate this directly. So once I calculate the updated values of torque and flux, now here I'm going to write TE and psi calculation. So now that I have all the values of voltages and currents with me, I should be able to calculate this. Now from here, the actual electromagnetic torque and actual flux linkage, those will be given to the comparator, and the comparator will compare the reference values of flux and reference value of torque with that of the actual values of flux and actual value of torque. Now I have the error with me. What is psi e? That is the error in the flux linkage, and what is the error in the torque. So let us now try to take a look at the sector positions what we talked about. So let me probably go back a little bit. I will show you a diagram where we are actually looking at the different sector positions of the flux linkage. So this is the flux linkage. So you can see very clearly that this is corresponding to V1, which is 100. This is V2, which is corresponding to, this is 612, 123, and so on. So we call this as sector 1. This entire thing from here to here we call as sector 1. From here to here we call as sector 2, and so on. So let us say I am currently going to have my flux position somewhere. Let me probably draw these vector positions here. So I'm going to have, these are the 6 voltage vectors that we are talking about. So this corresponds to V0. This is V1. This is sorry. This is V1. This is V2. This is V3. This is V4. This is V5. And this is V6. So these are the 6 vectors. And let us say I am starting with 0 flux in the first initial step. Maybe my psi s has come somewhere here. So this is going to be my psi s. And let us say this is my psi s. And if you look at the vector sector positions, I already told you that from here until here, it is sector 1. So psi s currently is in sector 1 position. When it is in sector 1, if I apply a voltage which is corresponding to V2 for a duration of delta t, I will have a voltage vector which is parallel to V2, something like this. So if I call this as V2 times delta t, this is actually going to have a resultant somewhat like this. So this is going to be psi s resultant. So if the resultant is obtained after applying V2 for a duration of delta t, the resultant is actually ahead of psi s by certain angle, and it is also slightly longer than the original psi s. So V2 being applied for duration of delta T increases the magnitude of psi s and also gamma. The angle gamma also increases. So when I'm talking about psi s lying in sector 1, applying V2 will increase the torque as well as flux linkage value. Now, rather than that, let me look at for the same psi s, if I apply V1. So let us say I am applying V1. V1 is like this. This is what is V1 times delta T. So if I apply V1 times delta T, I am going to have the resultant somewhat like this. The resultant is going to be somewhat like this. So the resultant gives me two things. One is the length is increased, but the angle it is put backwards. That is psi becomes, this gamma becomes negative. So I can say if V2 is applied, both the magnitude and the phase angle increase. If V1 is applied, magnitude increases, psi s magnitude increases, but gamma decreases. So if I want to increase the flux linkage magnitude, because the error says so, that I have to increase the flux linkage, but I want to decrease the torque, then I should be applying V1. On the other hand, if let us say this is my original value of psi s, and if I am applying, for example, V5 rather than V2, if I apply V5. So V5 is parallel to this. So I have to show V5 somewhat like this. So when I apply V5, so this is V5 times delta T. So when I apply V5, V5 corresponds to, please think about it, this is 6, 1, 2 switches are on, this is 1, 2, 3, this is 2, 3, 4, this is 3, 4, 5, this is 4, 5, 6. When I switch on 4, 5, 6, all the three switches simultaneously, then V5 will be applied. When I apply V5, both magnitude, that is magnitude is also decreased and phase angle is also decreased. So V5 is applied, then I'm going to have both magnitude of psi s and gamma decrease when I apply V5. Rather than that, if I apply V4, what happens? Let me try to take a look at that. So let us say this is the original vector position. This is psi s. So when I apply V4, V4 is somewhat like this. This is V4. So this is going to be V4. So when I apply V4, the resultant is going to be here. So this is psi s nu. So you can see that the length decreases. So if I apply V4, we can say that psi s magnitude decreases, but gamma increases. So when V1, that is the flux is in sector 1 position, applying 4 different voltages, applying V2 is going to increase both gamma as well as psi s magnitude. Applying V1 will increase the magnitude of the flux, but gamma will decrease. Applying V5 will decrease both, whereas applying V4 will decrease the magnitude but increase phase angle. Now, like this, for every sector position of the flux vector psi s, we should be able to arrive at what kind of voltages will increase the flux or what kind of voltages will decrease the flux, and simultaneously what kind of voltages will increase gamma magnitude, what kind of voltages will decrease gamma magnitude. So let us try to take a look at that. It is actually represented in the form of a table here. If flux vector magnitude error is positive, then we are going to have, at that point, we have to examine what kind of error we have in the electromagnetic torque. And if the flux vector is already in sector 1, we would be able to nullify the flux error as well as torque error by applying V2. We would be able to nullify the flux error, but if the torque error is 0, we should be applying V7, which is actually 0 vector. And if we are looking at flux error is positive, whereas torque error is negative, then we should be applying voltage vector 6, that is 456 or 561. We have to apply 561. So depending upon in which sector our flux linkage vector is located at present and how the values of torque error and flux error are manifesting themselves. Based on that, we should be able to decide which voltage vector we should be applying so that these errors are nullified. So, in general, direct torque control, what it requires basically is the actual sector position of psi s. So psi actual we are getting as calculation here from here. This is going to be sector position of psi s. So if I have the sector position of psi s, if I have the torque error value and flux error value, I should be able to select the appropriate voltage vector from the voltage vector selection table. And we should be able to fire the VSI devices accordingly, and we should be able to implement direct torque control easily. So the direct torque control major plus point in this particular case is we are directly looking at voltage vector selection from a lookup table, and all we are doing is only sensing voltages and currents. In fact, voltage sensing is also not essential because we have the switch positions from which we should be able to get the voltage calculated. Once I have voltage and current values with me, we should be able to get what is V alpha, V beta, I alpha, I beta, from which we should be able to get what is psi s value and what is the psi r value. So once we have this psi s and psi r, gamma, all those things, we should be in a position to decide what is the voltage vector, and then that essentially will allow us to fire the VSI devices. So direct torque control, the advantages, if I try to look at the advantages of DTC, we don't need the exact position of psi s is not needed. And one assumption that we are making is that psi r, because the rotor time constant is large, psi r takes time to respond. So by applying a suitable stator voltage, gamma can be adjusted. Because if we assume that psi r is not moving, if we are moving psi s forward, then we assume gamma is increased. If we assume psi s is moved backward, we assume that then gamma is decreased. So torque is influenced accordingly. So the exact position of psi s is not needed. The second thing, independently, TE and psi s are controlled by applying suitable Vs, that is stator voltage. And third thing we can say is psi s and TE are calculated directly from voltage and current values. But definitely there are disadvantages as well. So let me write about the disadvantages. One of the major disadvantage of direct torque control is psi s calculation depends upon resistance RS value. So parameter dependence is inevitable. It cannot be avoided at all. So parameter dependence is a major issue. Second thing we should say is we assume that psi r does not change within delta t. Whatever is the time duration we are talking about, we assume that psi r does not change. But that may not be true at low speeds, because in low speed, the frequency itself is small. So delta t also, the way it responds, psi s might also rotate at very low speed. Then psi r will have sufficient time to respond. So whatever we are assuming, that may not work very well. This is one reason why starting response of DTC is not good in most of the cases. Starting response may not be good at all in DTC. Third disadvantage we have to say is the same voltage vector is applied. Once you decide on applying V0 or V1 or V2 or V3, the same voltage vector is applied for the entire sampling duration. So sometimes the torque value and flux value can overshoot. If you see that the flux error is now positive, it can go into the negative direction in the next sampling time itself. So there can be overshoot in psi S and TE values. And last but not the least, one more disadvantage is current values are not being monitored. Current values are not monitored. So there could be large overshoots in currents. So on the whole, if we are sure that an AC motor drive is going to be run mostly at a larger value of speed and we want a very good dynamic response, in that case, direct torque control could be a very good candidate that can be employed. So in some of the electric vehicles, they are trying DTC and many industrial drives depend upon DTC. But large drives like traction drives and all generally employ field oriented control rather than direct torque control, because during starting you can have a lot of issues in direct torque control. But we said that generally we apply the same voltage vector for the entire duration, entire sampling duration. Rather than that, can we apply a voltage vector only for part of the sampling duration? So can we employ something like a duty ratio in that sampling duration itself? Only for 50% of the duration or 60% of the duration we want to apply a voltage. Can we do that? So that is one major research work that is going on even now in direct torque control. One more thing is what we talked about in terms of voltage vector. We only said there are 6 voltage vectors. That is because we are talking about only a 2-level inverter. Rather than that, if we use a multi-level inverter, we will be able to get several voltage vectors which are in between, rather than having all the voltage vector which is only of VD length. We can have several voltage vectors which may be 1/3 or 2/3 and things like that, and which may be dispersed all along the 360-degree angle. So what we talked about was this is, this is V1, this is V2, all of them are of VD length. Rather than that, can I have one more voltage vector which is probably lying somewhere here? One more voltage vector which is probably lying somewhere here. So these can be obtained in multi-level inverter configuration. So direct torque control, when it is implemented with multi-level inverter, it may be able to give much more accurate control as compared to what you see normally in our 2-level inverter case. So the research topics that are being pursued with respect to direct torque control are whether we can apply the voltage vector only for part of the sampling duration, which generally is termed as duty ratio control. And another one is multi-level inverter based direct torque control. So these are being pursued, quite a bit. So this concludes our topic of discussion on induction motor. What we had seen is we started basically with the principle of induction motor, starting of induction motor. We looked at braking of induction motor. That is all 3 methods: regenerative braking, reverse current braking or plugging. And we also looked at dynamic braking. In dynamic braking itself, we saw 4 or 5 methods. Then we came over to stator side control and rotor side control. In rotor side control, we looked at rotor resistance control and slip energy recovery. In stator side control, we looked at pole changing initially, then stator voltage control, then we looked at voltage and frequency control. In voltage and frequency control itself, we looked at voltage source inverter, which is implementing V by F control or scalar control. Then we had looked at current source inverter based control of induction motor for large capacity drives. Then we took a look at field oriented control and direct torque control using voltage source inverter.